Okay, in this lab, we're going to be looking at predicting types of chemical reactions and using that to figure out what the products of that reaction are going to be based on what the reactants are. So we're going to have 6 different little mini experiments that you can do at 6 different stations. And then you can kind of try the reaction for yourself. And then we're going to try and figure out what's happening at the atomic level based on the reactions that we're using and how they should kind of start to rearrange how they bond and things like that. Okay, so let's look at a couple examples. Let's look at station 1. Okay, so this is what you would do in the lab. You get a cup of aluminum foil, you add 20 drops of copper 2 sulfate onto the aluminum foil, you scrape them together, and you see if you can get some clues of a chemical change, maybe a color change, maybe a temperature change, and things like that. Based on how it looks, you might also get a clue of what your products should be. But overall, we can figure that out just by looking at the chemical the chemical formulas of what we start with. So let's look at what we're starting with here. So we've got 2 reactants here. One of them is copper 2 sulfate, and the other is elemental aluminum. So let's see here. So copper Roman numeral 2 sulfate is a compound made of copper. This Roman numeral 2 means that the copper has a positive 2 charge in this case. Sulfate is a polyatomic ion. It's sulfur loaded with oxygens, so sulfur and 4 oxygens. And sulfate has a negative 2 charge. Now, wonderfully enough, the positive 2 and the negative 2 should cancel out as is, so we don't need any more Cus or any more SO4s, so I can just put those together. And that's going to be the formula for my first reactant for copper 2 sulfate. Elemental aluminum is just Al. Now, if this was one of the guys in Hofbrinkel, like hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine, then I wouldn't just leave this as Al. I'd make it Al2 with a little subscript down there to show that it's diatomic. Those Hofbrinkel guys will bond with themselves to become a little bit more stable as an element, and it's still just bonded to itself and not to something else. But in this case, this is just monatomic. It's just Al because it's not one of those 7 naturally occurring diatomic elements. We should assume it's on its own. Okay, so our reaction type is going to be something that involves a pure element and a compound. So first thing we can just easily eliminate is decomposition. Decomposition would be just one compound that breaks down, so it can't be that one. Let's see. It can't be synthesis because that would be combining 2 very simple substances, like 2 elements. We have a compound in here that's a little too complicated to just shove aluminum in there. So it's not going to be a synthesis either. So decomposition and synthesis are out. Can't be combustion because we would need C's and H's reacting with O2, and we don't have any C's and H's, so that's not likely. So we're down to single replacement and double replacement. Single replacement happens with a pure element and a compound, whereas double replacement happens with 2 compounds that kind of switch partners. So in this case, since we have a pure element here, this is going to be a single replacement reaction. Single replacement. Okay, now in a single replacement reaction, we have that one lone element kind of bash its way into this compound and bond with one of these things, either the copper or that sulfate polyatomic ion, and then whatever's left gets kicked out as a pure element. So if I've got to pick whether the aluminum goes with the copper or with the sulfate, I just have to look at what charges they have. Aluminum on the periodic table has a charge of positive 3 as an ion. So if I have to pick whether it pairs up with the copper or the sulfate, I mean the copper had a positive 2 charge. The sulfate had a negative 2 charge. If I try and put together the aluminum and the copper to make a compound, positives and positives are never going to cancel, no matter how many Cus and Als they are. It's just not going to work. They're not going to make a compound. So that's probably not the best idea. Instead, I should probably get the aluminum to go and bond with this sulfate polyatomic ion and steal that from the copper, leaving the copper on its own. That's how our reaction is going to work, and this is how we predict what our products are going to be. All right, if we're going to kick out one of those things as just a pure element, it's going to be the copper, and that sulfate polyatomic ion is going to end up bonding with our aluminum here. All right, something that helps in basically all the reactions we're going to look at here, unless it's shown for you, like the whole reaction is shown for you, polyatomic ions are going to stay together. So a sulfate on the reactant side is still going to be sulfate on the product side. Ammonium is going to be ammonium on the left and the right. So unless I give you a reaction equation where the polyatomic ion changes, you can assume it's going to stay together as that polyatomic ion. It makes your life a little bit easier. Okay, write and balance the full chemical equation based on our reactants and our reaction type. So if we are dealing with copper sulfate reacting with aluminum metal, aluminum as an element, right? Again, we are expecting our aluminum to go hang out with the sulfate. So I'm going to pair them up. Al is going to be with the SO4. Now, I'm not sure if that makes a happy compound yet, so I'll have to come back to that. But for now, let's just write kind of the rest of the baseline of this. The other thing left is our copper that is now on its own. So when you go do this reaction for yourself, you might see a little bit of reddish brownish stuff down on the bottom of your cup on the aluminum foil. That stuff is copper metal. We're making just copper metal. We're taking it out of this compound and just there's copper now. And the aluminum ends up getting used up to make a new compound that doesn't look like aluminum. Okay, so the last thing we need to do before we can balance this is see how these charges cancel and see if we have the right formula here. So sulfate is a -2 charge. Aluminum is a +3 charge. Okay, so one of each of these is not going to cut it. I'm going to need to have some number of these and some number of these that get the charges to cancel. So one of these and one of these is not going to work. One of these and two of these is also not going to work. I'm either left over with excess positive or excess negative. If I want these to meet in the middle and cancel, I could probably get these both to +6 and -6. If I had two ALs, that would give me a +3 and a +3. If I had, scroll back down here. If I had, oops, I'm still on pink. If I had this whole sulfate thing 3 times, -2, -2, -2, that would be +6 and -6 canceling out, and all that charge goes away. That makes a happy ionic compound. So my formula isn't just AlSO4, it's Al2SO4 3, where that whole SO4 thing is together. I'm going to rewrite that S because that was a little sloppy. That's a little better. Okay, so I've got my reactants, I've got my products, everything is in the correct formula where either charges cancel or I'm following prefixes, which I didn't have any in this case. So now the last thing I have to do is balance this out. All right, so like for example, I have one copper on the left and one copper on the right, so that's okay. If I have one of these SO4s on the left and 3 of them on the right. So if I had a 3 here, it would mean I have 3 of these SO4s all together. I also have 3 of these coppers now. Okay, so I fixed the number of sulfates. That's good. I kind of messed up the number of coppers, but that's okay. I can fix that too. If I have 3 coppers on the left now, to match that, I need 3 coppers on the right. So I can balance that too. All right, let's see what else I got to fix. Well, aluminum, let's see, there's 2 aluminums on the right and there's only 1 on the left. So if I put a 2 here, 2 ALs on the left, 2 on the right, But now we're good on that too. So I've got my sulfates fixed, I've got my copper fixed, I've got my aluminum fixed. Everything's good. Any blanks I have left, I just drop a 1 in here. All right. So even without doing this reaction, as long as I know that I'm doing this between copper sulfate and elemental aluminum, I can predict that this is going to be a single replacement reaction, and therefore I should make this Al2SO4 3 and copper Cu. Okay. The rest of it I can fix with the balancing. Let's look at one more of these. Let's see. Which one should we do? Let's look at this one. Okay, so in this case, we've got a cup full of salt water. We use a battery touching some metal tacks on the bottom of the cup to send some electric current through the salt water. And we end up with a reaction, apparently. So let's see what that could be. Apparently, our only reactant is water. Now, I noticed, I mentioned there's like salt in the water and there's a battery involved, but those are just to get the kind of reaction going. Like how we might use a lighter to start a combustion reaction. Our battery is just there to kind of get the reaction going, to give it a little bit of a kick start. And the salt water is just there to help conduct the electricity through the water. So the only thing that's actually changing this reaction is water. So let's do, oops. Oh, there we go. Water is H2O. That's really the only thing I have to work with here. So my type of reaction is going to have to be decomposition. That's the only thing that only uses one reactant. It's like a dead giveaway. Decomposition. All right. So if water were to go through this decomposition reaction, if it were to decompose, what would happen? Well, I'm starting with only water on the left side of my reaction arrow, H2O. All right. I have my reaction arrow. And in a decomposition reaction, my compound is going to break up into the elements that make it up. So this compound is made of two elements. It's made of hydrogen, and it's made of oxygen. So I'm going to have those two elements made here. Now, I have to check and make sure these formulas are correct. Now, this isn't a compound, so I'm not canceling charges or anything. This is just a pure element in this case and in this case. So the only thing I have to check is, are these guys in Hofbrinkel? Are they one of those 7 diatomic elements? Well, the H in Hofbrinkel is hydrogen, and the in Hofbrinkel is oxygen. So these are both there, which means they don't just hang out as H or just O. They hang out as H2, and they hang out as O2. Okay, so be aware of those Hofbrinkel guys anytime you are dealing with elements. Okay, and if it's not in that Hofbrinkel list, it doesn't go diatomic. It just stays on its own, like the aluminum before. All right, and then to finish up the reaction, we're just got to balance it. Since now we have the right products with the right formulas, now we just have to make sure that we don't have any extra atoms or we don't come up short. So let's see. I've got 2 H's and 2 H's. That's good. I've got 1 O and 2 O's. So I need to have a 2 as my coefficient over here. So I can have 2 O's on the left side to match my 2 O's on the right. That also affects my number of H's. So actually now I have 4 H's on the left instead of the 2 I expected. So I got to fix this guy too. Put a 2 as its coefficient. 2 times the 2 H's gets me 4 H's to match the 4 H's over here. And then everything's good to go. So 2 H2O's should be able to break down into 2 H2's and 1 O2. And that's my full balanced chemical reaction equation for the decomposition of water. Okay, so in each one of these, figure out your reactions, get the right chemical formulas. Those are going to be the things on the left of your arrow. Figure out the type of reaction based on those reactants and how they're going to kind of come together. Whether we're using an element in a compound or a compound in a compound, just one compound, just two elements, or a bunch of C's and H's reacting with O2. Use that reaction type to predict what your products will be. Okay, and if you ever get stuck, on the last page, I have all the reaction types right here for you. You got synthesis, decomposition, combustion, single replacement, and double replacement, with some general forms of how the reaction goes that might help you switch around your atoms and get them to bond in the right way on the other side of your arrow.